Hi everyone. Thank you for joining my presentation. My name is Patrick Assuied. I'm a Director of Engineering and Platform at Elation Health. Today, I will be sharing our journey into modernizing our architecture and how Dapr was instrumental to accelerating our adoption of event-driven patterns. I hope this will inspire others to see how Dapr could empower them to do the same. First, I will go over our company and some context about our original architecture. I will describe some of our attempts we originally made towards a microservices architecture and some of the shortcomings we encountered. This led us to pivot into an event-driven architecture and selection of Kafka as our event streaming platform. This was a critical move that created new patterns in our company. It did, however, create some friction for early adopters and made it difficult to generalize the approach across the company. This is when we turn to Dapr and the PubSub building block in particular. I will elaborate why this made a huge difference. Finally, I will go over certain investment we made to bring Dapr to a larger audience, including the adoption of a flexible service template using Copier as its engine. Share some of our lessons learned and some of the future investments we're planning to make where Dapr will be instrumental. So with Elation. Elation is a relatively small startup founded in 2010 by Kina and Conan Fong, who saw an opportunity to help their father, an independent primary care provider, and many other physicians like him leverage technology to manage their patient care more efficiently. The core vision of the company is to create a future where primary care owns its powerful role in healthcare through technology-enabled innovation. Our user base is around 45,000 clinician users and manage about 23 million patient charts. Our engineering team counts a bit more than 50 engineers. Our original product is an EHR, electronic health record, which covers managing patient clinical records, integrations to lab and prescription vendors, but also front office for appointment and insurance management, a patient portal, and more recently, an integrated billing system. Our solution is fully hosted in AWS. The original code has been a monolith, internally called Hippo. It is a Python Django service with an RDS MySQL database. Asynchronous operations are powered by Celery tasks, which we also use to update the Elasticsearch cluster that powers the in-app search. In 2021, Elation saw a significant growth with multiple enterprise deals that funded additional hiring, increasing the size of the engineering team by 5x, and an investment in platform modernization. This led to the introduction of Kubernetes through AWS EKS, Terraform for infrastructure as code, and the adoption of other more modern platforms like Aura MySQL and Snowflake to improve our scalability. Given the growing size of our engineering team and the challenges that come with working on a single monolithic code base, this led also to our first foray into microservices as a way to increase our productivity. In our first attempt, we started pretty simple. Being a Python shop, we chose the most prominent Python microservices framework at the time, being FastAPI. We also opted for DynamoDB as a store. We didn't have a template, distributed framework of platform, so teams essentially all implemented their own flavor. The first team deployed to the AWS ECS offering. Then after the introduction of Kubernetes, all services were quickly moved to EKS. While we observed increased productivity as they allowed quick deployments to production multiple times a day compared to the weekly deployment frequency of the monolith, the lack of governance led to certain deficiencies. Introducing microservices without a proper vision and tooling typically leads to the creation of distributed monolithic architecture, where while services are deployed independently, they are highly coupled to one another, leading to higher brittleness. In certain use cases, these services aimed to migrate certain domains out of the monolith and therefore set up some synchronization, but led to dual write issues. The dual write problems occurs when two external systems must be updated in an atomic fashion. In our use case, we would save some information to the primary MySQL database and issue a call to the microservice. However, it is very hard to guarantee atomicity in this case, as each of these operations could fail and leave the two systems out of sync. This led this migration to never be finalized, as there was never enough confidence that data would not be lost during the migration period. Finally, introducing microservices highlighted a gap in observability as the more complex architecture required to track requests spanning multiple services. Without proper distributed tracing, troubleshooting such requests became very challenging. As a result of this early experience, we realized that we needed to decouple our services further. We also had multiple use cases that required real-time data replication. After some analysis, we opted for Confluent Cloud Managed Kafka offering. Since our monolith required too much refactoring to issue high-level events, we turned to Debezium and leveraged the outbox pattern to publish most of our system events atomically. For reference, the outbox pattern works by storing outgoing messages in a dedicated outbox table within the same database transaction as the main data change. A separate process then pulls the outbox table, in this case through the MySQL bin log, and reliably publishes these messages to Kafka. We also leverage some of the Confluent managed connectors, especially their Snowflake connector, to ingest data to Snowflake. For powering services, we searched through a compatible PubSub Python framework, but ended up just using the low-level Confluent Kafka SDK. While it worked well, it required a lot of heavy lifting to keep consuming threads alive, ensure proper retries, offset acknowledgement, and dead queue handling. If we wanted to generalize the approach for our engineering team, we essentially would need to either find a proper framework or build one ourselves. Many of us had been burnt out from previous experiences of having to build complex service libraries that required a ton of maintenance and also complex updates across entire service fleet whenever a critical library would be updated. This is also at the same time we acquired a company offering a billing system as part of our all-in-one strategy. The code base was in PHP, so whatever we would come up with would also have to work for that code base. If only a cloud and language agnostic sidecar technology existed that could help us simplify our setup. Well, this is obviously when we naturally turn to Dapr. After a quick trial, the simple programming model made sense to us. It plugged right into our Kubernetes infrastructure that was already composed of Argo CD, Keda, and Traffic. It had SDKs for Fast API and PHP, which made consuming events leverage the same techniques as handling HTTP requests, which felt very familiar to our engineers. It had great support for Kafka and ensured proper guardrails for event consumptions, retries, and dead letter queue handling out of the box. One thing it was missing was Avro support, though. As part of our early adoption of Kafka, we opted for leveraging their Avro schema registry offering, so all our events would be tied to a schema. This would make schema changes across services more predictable. So since it was missing, well, we just contributed to it. It speaks volume for how simple Dapr overall design is. Adding Avro support to the Kafka PubSub component took a week or two of development. And thanks to the great partnership with the Dapr community, it was made available to all within 3 months in the upcoming release. We quickly knew Dapr was the right move, but we still needed to simplify the adoption for our engineers. The next stage was to provide a simple process for engineers to create their new service with only the features they needed. We also wanted to ensure that teams could benefit from future additions or updates after their service was created. Most scaffolding tools do a great job of speeding up a new service, but any update is essentially manual. We discovered Copier, a Jinja-based templating tool that leverages Git to support upgrade capabilities. Another big concern was having to update and redeploy each service for every global change. For this, we turned to Helm charts. Our Argo City solution already deployed services through a shared service Helm chart. We updated this Helm chart so that Dapr components could be automatically added for all services through a simple Helm chart update. Team can still opt in for certain features or components or override our sensible defaults. But as a result of these two technologies, services could then be turnkey with Dapr in minutes, and our whole fleet could also be updated as needed in that same timeline. This setup also led to leveraging additional Dapr building blocks to help generalize features across our services in a decoupled fashion. An example use case presented itself as we introduced many services that required access to feature flag state. We make heavy use of feature flags to deploy features rapidly in a continuous delivery fashion and roll them out to customers as needed. Historically, only our monolith would be able to consume feature flags, since this is also where we built the admin tooling to manage their state. Whenever microservices needed to get this information, it was challenging or awkward to pass it through the service from the monolith. We also didn't want to introduce further coupling to the monolith by having services synchronously request the information from it. The combination of Debezium, Kafka, and Dapr made it very simple to replicate the feature flag state data into a DynamoDB state store. We could then automatically register the state component to all our services through the shared service Helm chart. Relying on the high availability properties of DynamoDB gave us confidence that each service could reliably access the data through Dapr. Dapr also allowed us to configure component-level resiliency policy and retry in case of an intermittent failure. But we still had to introduce a thin wrapper. Most of the logic is decoupled, and therefore the wrapper is unlikely to change often. Over time, we have converged into what we call an even first approach, relying heavily on eventual consistency. User HTTP requests get validated and directly published to Kafka using Dapr Publish. The events are then consumed by other systems, including the emitting service itself, to update its local data store. This allows us to use these events to feed our Snowflake data warehouse, Elasticsearch indexes, S3 stores, and whichever future use cases. This approach avoids the dual write issue, as the event becomes the system of record and guarantees ordering. To make this approach work, we rely on the ability to have multiple Dapr Kafka PubSub components within the same service, all set to a different consumer group. So the same topic can be consumed by a single service with different offset tracking. This complex setup would have been very difficult to implement without Dapr, but was easily adopted by all teams as the result of the simplicity of the component model. Over time, Dapr and this approach have enabled the following use cases: complex migration to microservices with zero downtime, new greenfield decoupled services, including an AI-powered ambient scribe integrated to our EHR, and many more. Let us dive deeper into one of the zero downtime migration use cases. As part of our EHR, we must allow providers and staff to manage patient demographics, name, date of birth, addresses, gender, emergency contacts, etc. As we expanded the scope and added patient insurance policy management, the team just followed the exact same design and added this information within a patient demographic resource. However, as the patient insurance policy domain became more and more complex with many business rules, the team felt it was time to decouple it altogether. Moving it presented many challenges. We wanted the change to be transparent to our customers, so existing public endpoints should still function after the migration. The migration should not follow a big bang approach, otherwise it would appear too risky. The diagram shows the original design. Having done prior investment to our event streaming platform, we already received all patient demographic changes into a snapshot patient demographic topic. We made sure to bootstrap the patient data so it retained all active patients in our system. In this initial phase, we could then spin up the new insurance API and consume the topic from the beginning to see the insurance database and enable it as a real-time replica. Once the replica was enabled, we could spin up the new insurance policy endpoints for the new service and start moving the system of record for insurance policies. The new endpoints follow our event first pattern, so they will publish an event upon receiving a valid put or patch or delete request. Because we wanted to roll it out gradually, we used our feature flag solution to identify the customers for which the feature was on for. When off, like featured here, the system would operate as before, where the monolith is still the system of record and the insurance API is still a simple replica. Once the feature flag is on, the insurance API is now a system of record, and the data is now replicated the other way into the monolith. This is to guarantee that any existing endpoint continues to work as a replica. Legacy public API write endpoint simply proxy to the insurance API for updating the policy, which publishes the insurance policy submitted event, which will be used to update both the insurance API DB and the replica. The same event is also synced into Snowflake as an audit log and for further reporting capabilities. What is next on our journey, you might ask? Dapr has truly enabled us to innovate faster and reliably. We keep finding use cases where it can help us. Recently, we've invested in bringing AI capabilities to our customers and having Dapr workflow orchestrate the long-running agentic interaction has been key. We have now also Daprized our monolith to bring some of the simplicity we brought to microservices to the larger code base as well. We have increased our observability by leveraging the out-of-the-box support, bringing Prometheus metrics to Grafana and OpenTelemetry to Datadog to power distributed tracing. Overall, it seems the Dapr community is reading our minds in terms of what capability we'll need next, and we feel more and more confident to include Dapr building blocks into our solutions in the future. Thank you very much for the time.